Hello everyone. Today we're going to be looking at solving a linear system of equations graphically. So remember from last class we looked at translating English sentences into basically the language of math, if you like. And that allows us to work with the information that we're given, and we can eventually solve the question that we're being asked. Now last class we just looked at confirming or verifying solutions to a system of equations. Today we're going to be looking at our most reliable way of solving a system of equations. Probably the easiest way, I would say. If you have a graphing calculator on you and you can isolate for one of the variables in the system of equations, then you can easily graph both and then simply find an answer. So we'll see how that's done right now. So starting with the brain warm-up, might be a good idea for you to pause the video at this point and try the brain warm-up on your own, but we'll go through that right now. So in the relations and functions unit, we learned that there are many ways to describe a relation. Two important ways to describe a relation are with equations and graphs. So two different equations showing the relationship between x and y are shown. So this is just an example. Relation number 1, y equals 3x minus 1, and relation number 2, y equals 1/2 x plus 4. So to satisfy equation for relation 1, each y value can be determined by multiplying each x value by 3 and then subtracting 1. And to satisfy relation number 2, we multiply each x value by 1/2 and then add 4. So if we're going to graph those, graph relation 1, so 3x minus 1. So the y-intercept is at -1. The slope is 3/1, so we got to go up 3 and right 1. So that'll be the next point. And then we got to go up 3 and right 1 again, and up 3 and right 1. So we can connect those points. Sorta. So that's what relation number 1 looks like roughly. And relation number 2, 1/2 x plus 4. So the y-intercept is here. And the slope is 1/2, so we go up 1/2, up 1/2, up 1/2. So let's go ahead and draw that line. Kinda trying to get it parallel. Alright, so there's relation number 2. Number 1 and number 2. Okay, so done. Looking at the graphs, what's the only combination of x and y that satisfy both? It's got to be here. So where they coincide, which is at 2, 5. That satisfies both equations, right? So any point you choose along number 2 will satisfy relation number 2, and any point you choose along number 1, say for example 0, -1, or I don't know, it's probably -1, -4, those are all satisfied, all satisfactory choices for number 1, and a number of satisfactory choices for number 2, but the only place where they match up, where they line up, is where they intersect. Okay, so what's the only combination of x and y that satisfy both? 2 and 5. So your answer to the last question is what we call the solution to the system of equations. So therefore the solution to the system of equations described by these two equations is 2, 5, or x equals 2, y equals 5. So let's verify by inputting the point of intersection into each equation and assuring both sides of the equation are equal. So we are verifying. So starting with 3x minus 1, we're going to plug 2 everywhere we see an x, and we're going to put a 5 everywhere we see a y. Okay, so that's 5. 3 times 2 is 6, minus 1. So does 5 equal 5? Yes, it does. So that one works. And for the other one, 1/2 x plus 4, same idea. Put a 2 everywhere you see an x, put a 5 everywhere you see a y. So 5. And keep in mind, we're not trying to, like, quote unquote solve this equation. We're just verifying. So we're keeping the left side, all the stuff on the left, off on its own, and all the stuff on the right off on its own as well. So we're not trying to mix these or solve for anything, because there's no variable that we need to solve for. So we're just evaluating both sides independently and checking that they match up. So 1/2 times 2 is 1, plus 4, and 5 is indeed equal to 5, so both equations work. So this is probably the most straightforward way, I would say, to solve. It's a good backup. So if you're ever down the road and you find yourself having difficulty solving things like algebraically, or you're unsure of your solution, that you get through, which you'll see in a moment, substitution or elimination, you can always fall back on this and verify that your solution is adequate. So remember, to solve a linear system of equations means to determine values that satisfy both equations. Therefore, when using graphs of linear equations, the solution to the system is the point that lies on both graphs. So it's the intersection. A linear system displayed graphically is a quick way to see the solution visually. Remember to label your graphs with their respective equations when solving graphically. So the intersection is the solution. So with the system of linear equations, the intersection is the solution. Okay, moving on to number 1. Graph the relation x minus 2y minus 6 equals 0 by determining the x and y intercepts. Label the line. So we've done this a little bit last unit. So to figure out the x-intercept, so we have an equation in general form, right? So the x-intercept happens when y equals 0, so we can just put y equals 0 here and figure out what x should be. So it'll be x minus 0, so 2 times 0 is 0, and then minus 6 equals 0. So x equals 6. That's where that one happens. And the y-intercept we need as well. So that one, y-intercept, happens when x equals 0. So I put 0 in there. So then I'd have negative 2y minus 6 equals 0. I'll maybe bring this to the right, so I'll have negative 6 equals 2y. Divide both sides by 2, gives me y equals negative 3. Alright, so the y-intercept then will be here for this one. So let's draw that. Okay, just adjust that a bit. Okay, let's maybe just label that as A. And next we'll do this one. figure out the x. Oh, okay, so this one it wants us to rearrange into slope y-intercept form, so I guess we can do that too. So we need to get y on its own. So I can, okay, so we'll have 2y. I'll subtract x from both sides, giving me that, and I will add 2 to both sides, giving me that. And last I need to get rid of the 2, so I just need y on its own. So I'll have negative 1/2 x plus 1, right? 2 divided by 2 is 1. Okay, so that's the y-intercept of B, and we have the slope as well. So the y-intercept is there. The next point we will have, we'll get by going down 1, right 2, and then down 1 and right 2, down 1, right 2, and so on. So let's draw that. So there's B. Okay, good. So now we need to state the solution to the system. So that one's A, that one's B. The solution happens where they intersect. So that seems to occur at 4, negative 1. That's where they intersect. So 4, negative 1. And now let's verify. So let's check that with each. So for the first one, x minus 2y minus 6 equals 0. So I'm going to put that everywhere I see an x. I'm going to put negative 1 everywhere I see a y. So 4 minus 2 times negative 1, subtract 6 equals 0, hopefully. That's what I would expect. So 4 subtract negative 2. So 4 subtract negative 2 minus 6 equals, hopefully, 0. So 4 subtract negative 2 is like 4 plus 2, which is 6. 6 minus 6, 0 equals 0, true statement. Okay, and for the second equation, we go x plus 2y minus 2 equals 0. Put a 4 in for x. Put the negative 1 in for y. And confirming that that equals 0. So it'll be 4 minus 2 minus 2. That will add to negative 4. So 4 subtract 4 is 0. So 0 equals 0 is another true statement. So we did it. Okay, moving on. Graph the following equations. So 2x plus 4 and 2x minus 5. So plus 4, that's the y-intercept. And the next point, so it's 2 over 1 is the slope, so up to right 1, up to right 1. I guess we could go down to left 1 to get the previous, and down to left 1. Right, and 2x minus 5, so the y-intercept down here, up to right 1, up to right 1, up to right 1, and so on. So let's draw. So that's pretty close. And the next line. That's better. Okay, so what do you, well, what's special about them? It looks like they're parallel. How many points lie on both lines? None, right? Parallel lines will never meet. So you could go as far in that direction as you want. They will never touch. And you could go as far that way as you want, and they'll never touch that direction either. So because they never touch, it's there's no solution, right? The intersection of two lines in a system of linear equations is the solution. Because there is no intersection formed by these lines, that means there's no solution. Okay, another one. So negative 2x plus 4 and this one here. So let's maybe just graph this right away. So 4 is the y-intercept, negative 2 over 1. So negative 2 over 1, negative 2 over 1, negative 2 over 1. So let's connect them. Whoa. Did not mean to type that. There we go. So that's that one. And 6x plus 3y equals 12. I guess we could try to find the x-intercept. Maybe I'll convert it to slope y-intercept form. So this would be 3y equals negative 6x plus 12. Got to divide by 3. So y equals negative 2x plus 4. And that's identical to that one. So we would just have an overlapping line. So maybe I'll do, so they'd be overlapping. Like, so that's that one. Okay, what's special about the lines? They are parallel, but they are also overlapping. Or I guess another way to say that is they're identical. How many points lie on both lines? Well, wherever you go, any point that you pick on here will automatically be on this one as well. So you could pick any point in as far as you want to go in that direction and as far as you want to go in that direction. Any point you can imagine that exists on this one will also be on that one. So there are infinitely many. They intersect everywhere that they exist. So what's the solution? Infinite solutions. So long as it exists on both lines. So for example, e.g. 0, 4, we could also pick, I don't know, forget what else, 2, 1, and so on. Like we could just, you could keep going. And it doesn't even have to be just restricted to integers. You could pick, as long as it's like, yeah, as long as it lies on both, it's a solution. Okay. I mean, you always have your graphing calculator with you in this course, so you might as well take advantage of it. Certainly saves you some time in terms of graphing everything by hand. So when you are solving a system of equations with your graphing calculator, you need to get it in the form y equals. So you'll have a couple equations. You need to get them both so that one variable is on its own, because that's the type of input that your calculator accepts. Yeah. So if you, if you went on Desmos, you can just as easily type, well, what was the ones that we just did. So if you wanted to, you can type it just as it is in Desmos. So I guess this is just a little plug for that. Y equals negative 2x minus 4. So you could type that in and it'll graph something for you. And you could also type this into one of the fields and it'll graph that line for you just as well. Your TI calculator will not accept this as an input because it has like your Y1, Y2, Y3, and so on. So it's looking for that format. So that's what you need it to be. Y equals something. So it will not accept that as an input. Okay, and then we can find the intersection point. In Desmos, they'll just graph automatically, and you can just move your cursor over the intersection point and it'll just tell you. It'll be like, okay, that's at 1, 4, for example. With your graphing calculator, it's not that much more difficult. You just press second and then calc, or second trace, and then choose 5, which is the intersection. Use the left right arrow key to move the cursor to the point of intersection. First curve, enter, second curve, enter, and then tell it to guess, press enter, and the X and Y coordinates of the point of intersection will appear. So that's what we got to do. So let's try with this system. Okay, so given this system, y minus 9 equals 3x, and 2x plus 3y equals 5. We're going to solve that using our graphing calculator. So state your graphing window and draw a sketch of the graphs. So this one, we need to get it in a form y equals something, so we should get rid of this 9. So simply just need to add 9 to both sides, so 3x plus 9. And then for this one, again I need y on its own, so I can start with 3y equals negative 2x plus 5, so I just subtracted 2x from both sides. And then I got to divide both sides by 3, so y equals negative 2/3 x plus 5 over 3. Right, got to divide the whole thing by 5. So this gets divided by 3. Sorry, got to divide the whole thing by 3. That gets divided by 3. That gets divided by 3. And same with that. So everything's over 3. Alright, so let's bring our calculator into the picture. So 3x plus 9 goes there, so 3x plus 9. This one, so negative 2/3 x plus 5/3, 5 divided by 3, and 9. Okay, and graph it. Alrighty. Okay, so good. The intersection point is on our screen. Thankfully, we don't have to adjust the window, so we might as well just keep it as is. And so I guess we need to find our window settings. So our window is negative 10, 10, 1 for both x and y, so just in that order. We'll remember that. So back to the graph. We need to find this. So if this was Desmos, I'd just move my cursor over that and click there, and it would tell me. But we need to do, there is no touch screen on this yet. So what we need to do is kind of get that close-ish to the intersection point, hit enter. It automatically selects the second curve, hit enter again, tell it to guess, and there's the intersection point. So at negative 2, 3. So my window was negative 10, 10, and 1, negative 10, 10, 1. So y, or x min, x max, x scale y min, y max, y scale. The solution was negative 2, comma 3. Okay, so 3x plus 9. So something, what did it look like again? So, okay. Alright, and then, so maybe just draw it roughly. So that was 9, that was 3. Y equals 3x plus 9. And yeah, so this one, something like that. Just kind of freehanding it. You don't have a grid drawn here, so that looked to be roughly what we were dealing with. Negative 2/3 x plus 5/3. So this was negative 2/3. Okay, pretty straightforward. Yeah, usually your most reliable way, so if you're ever uncertain about how to solve these in the future, you can always fall back or at least verify your solution graphically. Okay, so let's try a couple more. State the solution to the following systems of equations. Use graphing technology, round any values to the nearest tenth. So yeah, you might want to try these. You can probably pause the video and try each of these out. So remember, you got to get it into y equals, graph each, put one in for y1, put the other in for y2. Hopefully the intersection point lands on your screen. If not, then I guess you got to adjust the window. So this one I'll have to write as y equals 2/3 x plus 17/3. And then that one's good to go. So let's go ahead and type those in. So 4x minus 3 I can put in for that one. 4x minus 3 goes there. And what was it? Negative 2/3 was it? Or just positive 2/3? Positive 2/3, that's what it was. 2/3 x plus 17 over 3. So 2/3 x plus 17 over 3. So I'm just putting each of those fractions in brackets just because I don't know, sometimes it'll do something funky and it might think that you want to, I don't know, have the x in the denominator with the 3, or yeah, I don't know, any number of things could happen. So I usually just like to put brackets around each of these things so that it knows to deal with them kind of separately. So let's graph that. And there's one. There's another. And let's find the intersection point. So second trace, go down to intersect, press enter, select the first graph, select the second graph, tell it to guess. There's the intersection point, 2.6 and 7.4. And I think what I might do, oh, maybe I can't. Never mind. I could save some time by taking a screenshot. So 2.6 and 7.4. So maybe just do a rough sketch of each line, kind of like something like that and like that. So this one was your 3y equals 2x plus 17. And this one was your y equals 4x minus 3. I didn't change the window settings, so minus 10, 10, 1, minus 10, 10, 1. Okay, try this one now. So again, we need to get y on its own. So we'll have y equals x minus 12. So add x to both sides, subtract 12 from both sides, we get there. For this one, minus 1/3 x, so I just brought that to the front, and then 6 plus 1 will be plus 7. So that's what I need to put in for my equations here. So let's do that. X minus 12, and negative 1/3 plus 7. Graph that. Okay. Alright, so you can see they're sort of converging. It's going to be maybe over here somewhere. So if we boost, like if we make this further, this boundary, if we push it further to the right, we should be good. So maybe let's bump x max to like 15, see if that's enough. Okay, not quite. Let's maybe try 25. So that looks to be sufficient. So let's just maybe double check. So x minus 12, negative 1/3 x plus 7. Oh, negative 1/3 plus 7, that was my issue. So, oh, second delete, so I can put an x in there. Negative 1/3 x plus 7, that's what I was looking for. I thought that looked a bit suspicious. Let's see that. Now it might be better. Yeah, that's a bit more normal. So maybe I'll keep 25 as my max window setting. Find the intersection. Go down to there. So 14.25 and 2.25 is the solution. So 14.25 and 2.25. My window settings, negative 10, 25, and 1. And y settings, negative 10, 10, and 1. So what that looks like on the graph. Okay, a bit like that. So let's do quick sketch. Something a bit looking like that. So this was our y minus 1 equals 6 minus x over 3, and this was our y minus x plus 12 equals 0. This point here was 14.25 and 2.25. Okay, moving on to number 3. 10-kilometer race taking entry fees of $5 per student and $9 per adult. During the first hour, 32 people entered the race, and a total of $180 was collected. Determine how many students and adults, whatever, entered the race during the first hour. Define your variables. So, how many students and adults? So, I mean, you can pick any variable you want, but because we're going graphically for this eventually, it might help to stick with X and Y because that's what your calculator accepts. So let's maybe just go X equals the number of students and Y equals the number of adults. So next we're going to write a linear system that models the situation. So we're going to need two equations. We've got one equation dealing with money, right? $5 per student, $9 per adult, $180, and we have 32 people. So the number of students and adults need to make 32. So X plus Y needs to add up to 32 and $180. So now we're dealing with costs. So notice this is number of people, another number of people, and a total number of people, right? So the units across this equation are consistent. For the next one, we want to deal with dollars. So for example, if one student and one adult showed up, we would make $14, right? We didn't make 14 though total, it was 180. So if we adapt this, I mean, we could have like 2 students and 3 adults, like any number of possibilities could be for the number of students and adults. So if I make this more general, I would have 5, maybe skip the bracket, 5x plus 9y equals 180. So there's our system of equations. That gives us a number of dollars, 5 times the number of students, 9 times the number of adults, equals 180. So if I want to graph these, I should get y on its own. So y equals 32 minus x, and this would be y equals, so gotta do a few steps in here. So negative 5x plus, maybe I'll just leave that 9 there for now, plus 180. So I got to get rid of this 9 now. So y equals negative 5, 9 x plus 20. 180 divided by 9 is 20. So I can put that in for y2. I can put that in for y1. And now I can solve it graphically. So let's go ahead and put that into our graphing calculator. So I have something for y1 and I have something for y2. So 32 minus x is the first equation, and negative 5/9 x plus 20, negative 5/9 x plus 20. Let's see what we got. And interesting. Okay, so I mean, at least we've got 2 lines here. Sometimes you graph it and it's just a blank screen, so you got to kind of try to figure out where to go. So it looks like if I bump this up quite a bit and I bump this to the right quite a bit, I might be able to see where these 2 points intersect a little bit more clearly. So let's bump the y max, so the upper limit, up to, well, the y-intercept there is 32, the y-intercept there is 20. They both have negative slopes, so it looks like the most we would have to the right of the y-axis is 32. So I guess we could pick like 40 or 50 even. 50. And again, it looked like we needed to go further to the right as well, so maybe if we bump this up to 50, should cover it. Alright. That looks pretty decent. That looks about what we have here. If you don't want the ticks to be so closely spaced, you can maybe change that to every 5. So then it looks a little bit cleaner. Okay, we need to solve or find this intersection point. So second trace, number 5, so the intersection. Enter on the first curve, enter on the second curve, tell it to guess. 27.5. So 27.5. So quick sketch. I forget what it looked like already. Okay, so all right. Something kind of like that. Okay, this was 32, that was 20, this graph was, maybe I'll write it, I mean you could write it as it was originally. 5x plus 9y equals 180, and x plus y equals 32. So what does that mean? 27.5, remember we defined x as the number of students. And the number of adults was y. So number of students is 27, number of adults is 5. So 27 students and 5 adults. What's the question again? Determine how many students and adults entered the race during the first hour. So entered the race during the first hour. Okay, summary for the day. System of linear equations will have only one solution if the slopes of the lines are different or unique. Graphically, there will be one point of intersection. A system of linear equations will have no solution if the slopes of the lines are the same and the y-intercepts are different. So that's a situation where the lines are parallel. There will be 0 points of intersection, which means the lines are parallel. A system of linear equations will have infinitely many solutions if the slopes are the same. And the y-intercepts are also the same. So graphically the lines will overlap, which are called coincident or dependent lines. Alright, that's it for the day. You can try this out. Solve each system. So, I mean, each of these are already isolated, looks like, okay, but these ones might take some work. So you got to get these, get y on its own for those, and you can solve all of these graphically and then match them up along there. Is there any other questions for you to do? No, that's on to substitution. So you can do that for today. Don't forget to try out some of the practice questions in your textbook, and I'll see you next time.